1500 here. Let me update you on some things that I've decided to do differently. First of all, you're going to think that I've lost my mind this week, or at least this kind of segment, because your assignment for this week is kind of crazy. You're going to have an assignment from section 3.3, 6.1, 6.2, 6.3, and 6.4. Now you're probably thinking, Darville, you've lost your mind. Actually, I haven't. Well, maybe I have, but I really don't think I have. This is 5 sections, but what I did as I went in, some of this material is a lot easier. And also I went in and instead of, given like the 17, 18, or 20 questions that the textbook recommends, I gave 5 questions or 8 questions, very minimal questions per section. So, there is going to be some. I'll tell you what. Let me see if I can get this. The focus isn't really suiting me for some reason. Okay, so again, there's going to be enough, but it's going to be a busy week. But it's just the things that we have to do sometimes. One other thing I want to tell you: the due date from here on out are going to be changing. The due dates will be Monday at 11:45 p.m. instead of Sunday. And the reason I'm doing that is, I realize as students that we procrastinate. I know when I was a student, I procrastinated. My wife was one of the darndest procrastinators I've ever seen. And with these assignments being done on Sunday, I'm getting a lot of emails on Sunday. And guys, I don't work on Sunday. Sundays, I always say that Sundays are my F day. That's for my faith, it's for my family, and it's for me to have fun. So Sunday afternoons, we're usually on the lake or on our kayaks or doing something like that. Sunday mornings, I'm always in church. So we get home, right around 12:15, 12:30, eat lunch, spend time with my family, and have fun with my family in the afternoon. I'm not going to check email very often on Sundays. Now, you might say, well, you responded to an email one Sunday from me. Well, I do sometimes. If the girls are like getting ready to go out on the boat and they're taking too long, I may jump on the computer and maybe answer a few emails. But guys, typically I don't work on Sundays. So I thought because of that, it's going to be fairer to you if we change these due dates to Monday instead. And there may be a week coming up that we might have to adjust that a little bit, and I'll do so if that's fair for you. But from now on, let's just go ahead and unless told otherwise, due dates for assignments will be Monday at 11:45. So that way, if you contact me on Monday, I check my emails quite regularly during the week, and even including Saturdays, but I don't check it regularly on Sundays. What to do? Let's say that you're just finding statistics challenging, and you need some help. I think, as I told you in a previous video, you can come see me. You can set up an online session with me through Google Hangout or Adobe Connect. And the fact that does it drives me absolutely insane, where that squeezes in for some reason. But probably the best way is to go to the math lab. And the math lab, just about all through days, Monday through Friday, from approximately 8 to 4. This is staffed by not only math majors, but my graduate assistants for the graduate program. I think I've told you before, just to reiterate this, Melissa and Allison are the GAs, and they are there to help you. Now, if you've never been to our math lab, here's kind of what it looks like. If you take a look at Massey Hall, where this is the front, Massey Hall is actually attached to the administration offices. In fact, this is where my office is. If you come through this hallway, right to the right, you're going to see the dean's office. We'll keep coming down the hallway, and there's some restrooms right over here. But there's a hallway that goes back to the right. It actually kind of comes around this way. Now my office is back in here. But if you'll turn down this hallway, the first room that you see on the right is the math lab, and that's where Allison and Melissa hang out throughout the day. So sometimes both are in there, sometimes just one. But anyway, this gives you a chance to get some free tutoring if things aren't going well and you can't make it to campus on the days that I'm there, or you just don't really want to do that whole online office hour thing. But remember, I'm available 2 hours a week for online office hours if you'd prefer to meet with me. All right, guys, got a pretty cool video today. This first one, we're still going to pretend or assume that we're dealing with a sample. But the things we want to talk about here are location of particular values within the sample. And what we're going to look at here are something called z-scores. And your book refers to those as standard scores. And we're also going to look at percentiles. And I'm also going to go through just a little bit more about a box plot. Okay? So first thing we need to do is let's get some data. And I've already done that. And what I'd like to do here is I would like to concentrate on this thigh measure. So they run 43.1 down to 51. So the first thing I'd want to do is enter my data, as we've done before. I can see I got some data in there I want to get rid of, so I'm going to highlight L1, go clear, enter. So now comes the tedious part, is typing these 20 numbers in, which is always no fun. Actually need some music here. So I'll call these out. 54.3, 42.2, 53.9, 58.5, 52.1, 49.9, 53.5, 56.6. This is boring the crap out of me. I love statistics, but I hate typing in these numbers. 56.7. Did that really come out? 46.5. 44.2. 42.7. 54.4. 55.3, 58.6, please hurry up before I lose my mind, 48.2, and 51. All right, I'm supposed to have 20 numbers. I'm going to go back through and just check 51, 48.2, 58.6, 55.3, 54.4, 42.7, 44.2, 46.5, 56.7, 56.6, 53.5, 49.9, 52.1, 58.5, 53.9, 42.2, 54.3, 51.9, 49.8, 43.1. Cool. All right. So guys, I'm going to close this. I'm going to be done with Excel. And I'm just going to focus on the calculator now. So I have my data installed, or I have my data entered in the calculator. And I am going to save the emulator state just in case. This is, what was that, thigh measures. And I'm just going to save this to the desktop just in case something happens like it did last time where there was too much going on the calculator and it shut down on me. Okay, because I don't want to do that again. I don't want to have to go through and type things. All right, guys, I got a text I need to take care of. My stepmother was rushed to the hospital this morning, and yeah, looks like she's going to be kept in the hospital. So guys, let's just talk about a few things. All right, so let me get out of here and go back over here. What a z-score does, it's one of the most important measurements that we'll talk about. A z-score simply calculates the difference in a score and the mean in standard deviations. Now, let's think about that. Why is it important to calculate the difference in a score and the mean, not just in just a distance, but in standard deviations? Well, guys, if we have a distribution that has a mean of 50 and a standard deviation equal to 2 versus a mean of 50 with a standard deviation equal to, say, 10, where does a score of 55 fall? Well, when we have a standard deviation of 2, this is saying that we have a distribution that's centered at 50, but the spread around the mean is only 2 units. So the average spread around the mean is only 2 units. Whereas if we have a mean of 50 and we have a standard deviation of 10, we have a distribution that's centered around 50, but the average spread around the mean is equal to 10. Well, guys, what we have is we have a measurement in statistics called z-scores or standard scores that allows us to take a score from a distribution, subtract the difference from the mean, so see how far it is from the mean, and divide out in terms of the standard deviations. So guys, in the first situation I talk about, the z-score for 55, when the mean is 50 and we have a standard deviation equal to 2, I got too much going on here. Let's so the z-score for a score of 55 when I have a mean of 50 and a standard deviation of 2 is 5 over 2, which is 2.5. So this tells me that a score of 55 is 2.5 standard deviations above the mean. Whereas a score of 55 with a standard deviation equal to 10 is just 1/2 standard deviation above the mean. So we could say here that a score, obviously, of 55 is 1/2 standard deviation above the mean. Now, so z-scores give us an indication, if you will, if we've got this bell-shaped and symmetric distribution, or actually any distribution that we get from a histogram, the center of that distribution is going to be somewhere around the mean. The standard deviation is the measure of spread around the mean. So if we have something that's close to the mean, then its z-score will be smaller positive than another score that, say, is up here, which is further away, more standard deviations away. Scores to the left of the mean are below the mean, so they're going to have a negative z-score, and the magnitude of that difference just tells us how far away in standard deviations that the score is below the mean. Okay, now let's get our hands dirty here, and let's go into this this distribution of thigh measurements. And just for the heck of it, let's just come down and let's just concentrate on this 42.2. So someone so one of the participants of the 20 people who gave thigh measurements, someone had a 42.2. Well, guys, what I would need to do is I'd need to go into Stat and go over to Calc, go one variable Stats, go to L1. I don't have a frequency distribution, so I don't need frequency list, and I need the standard deviation. So I'm going to close this up a little bit so I can go split screen on you here. All right, so when I come over here, I can see that for this distribution of thighs, has a mean equal to 51.17, and we have a standard deviation equal to 5.23. So what I can determine here, the thigh measure of x equal 42.2. I have no idea why I wrote 42.4. Has a z-score equal to the following. Now, guys, when you put this in your calculator, you have to pay attention to order of operations. So I'll have 42.2 minus 51.17 divided by the standard deviation, which is 5.23. So we can say that the person with a thigh measure of 42.2 has a z-score of negative 1.72. So this person thigh measure of 42.2 is 1.72 standard deviations below the mean. Now, as we look through our data set, we can see that not all scores are below the mean. That's one thing that drives me crazy about these testing people with our state of Kentucky and state of Ohio, these high stakes tests. These state tests. It seems like they want everyone above the mean on these measurements, which is extremely goofy. But anyway, if I come all the way down here, I see that one participant here had a measurement of 58.5. So this particular person's thigh measurement can easily be calculated as 58.5. So I'm going to use this feature here where I just go second function entry, because all I need is to change the first measurement, 58.5. The mean and the standard deviation are the same. So what did I do? Did something goofy here. No, I didn't include the parentheses. Well, as it turned out, it would have been easier to not take the shortcut. So let's insert the parentheses there. All right, so that should work. So this person's z-score measurement is 4.0, and I can just really just use the interpretation I have up here. So this person's measurement, not of 42.2, but of 58.5, is 1.40 standard deviations. I guess since the standard score, the z-score is positive, it would be above. So guys, z-scores give us a way to compare scores to the mean in terms of their distance from the mean in standard deviations and not just directed scores. So this actually turns out to be nice in situations where we have scores that come from different distributions. So let's say that, at SSU, let's say that we have, I don't know, of entering class, let's say that we have 600 students that has a mean of 22.1 on the ACT and a standard deviation of 5.1. So gang, this is the ACT, and not as many people take the SAT, but let's say the SAT has an average of 1,008 with standard deviation of 204.5. And this is the SAT. Well, let's say that John took the ACT and he scored a 24. And let's say that Amy took the SAT and scored a 1200. Now, and we want to know who scored the best relative to the other students here at Shawnee State University. So we've got a sample of students here. And we have the sample mean and sample standard deviation in both of these. Well, guys, what we could do is we could calculate the z-score for John. So his score of 24 over 22.1 over 5.1. So we can put that in our calculator. Guys, I'm just going to put it in my calculator that I have here. So John's score is 0.37 standard deviations above the mean. What I would do next is I would calculate Amy's z-score. So she scored 1200 out of a distribution that had a mean of 1,008 with a standard deviation of 204.5. So it looks like her z-score, and this is one of the key features of a z-score, is being able to compare scores from different distributions. So Amy's z-score turned out to be 0.94 standard deviations above the mean. So relative to their own distribution of scores, Amy scored higher than John. Okay, So again, that's one of the important features of, um, of being able of using z-scores is to compare scores from different distributions with different means. Now, let's talk a little bit about percentile. And percentile by definition is just the percentage of scores at or below. Now, typically, we focus on the below portion of this, but it's the percentage of scores at or below a given score. Okay, now the mean and standard deviation don't come into this as much. What we do is we order from low to high, and just find out a relative position based on percentile ranking. So the percentile for the thigh measure. Why do I keep putting 42.4? For 42.2, well, gang, what I would do there is I would go back to my calculator. I'm going to make this larger. And I would go to, I would appreciate that I have my information in L1, so I would go to Stat. And I would come down to number 2, and I would go Sort Ascending. So I want to sort ascending the values that I have in L1. Now when I go back to Stat and go to List L1, I can see that I have these things in ascending order. So 42.2 would technically be at the 0th percentile because there's no scores below 42.2. So that was a horrible example. Let's come up here and, guys, I'll tell you what, hold on just a second. I have someone is at the front door, and it's probably the UPS guy. All right, guys, sorry about that. I just consider your professor stepping out of the room. Okay, so let's choose something a little bit more interesting. Let's say that we would like to find the percentile ranking for this 49.8. So what I would do is I would notice that there, again, we have, 20 scores here. So I would notice that at 49.8 that there are 1, 2, 3, 4, 5, 6 scores below. So 6 out of 20. Don't you wish it stayed this easy the rest of the semester? So 6 out of 20 gives me 0.30. So I would say that a score of 49.8 is at the 30th percentile. Now, what if I wanted to find a score at a particular percentile? So let's say I want to ask a question, what thigh measure is at the 62nd percentile. Well, that's going to be pretty easy too. Actually, not difficult at all. I would say that I have 20 measures. I've got them in ascending order, so I would multiply that by 0.62. So 20 times 0.62 gives me 12.4. So I've got to think about this as the 12.4th position. Well, I can't be at a 12.4. I can be at the 10th position, the 11th position, the 12th position, the 13th position. So guys, what I would have to do is I would have to go up to the next position, find the number at the 13th position, with which your calculator is going to be very, very, very easy. So a score of 53.9 would technically be at the 12th point, or I'm sorry, at the 62nd percentile. It would also be at the 63rd percentile. So when we get small data sets, there's the same score can take on multiple percentile levels. Now we're going to get into something here probably in the next video where we look at measures from populations. Again, we're focusing on measurements from samples right now. So we're going to get into measurements of location for populations, which become a lot more interesting. But nevertheless, we're still thinking about just describing samples. All right, guys. I want to go through one more thing with you, and that's how to do a box plot. And I want to do one of these by hand. Not that we would ever do one of these by hand, but I want to just to show you some features of these box plots. So, guys, if we're going to do a box plot, what would we do? Well, the first thing you're going to want to do is to appreciate that a box plot consists of the 5-number summary plus outliers. And then finally, you're going to want an appropriate axis or appropriate thing to place your graph on. So let's do that. All right, so I'm like to do things the easiest way possible. So my 5-number summary, I'm going to use the calculator to get it. So I have my information in L1, so I'm going to go over calc, one variable stats, frequency. We're not going to have a frequency list, so go calculate. And I'm going to scroll down to the bottom, and I'm going to write those 5 numbers down. So guys, the 5-number summary is 42.2, 47.35, 52, 454.85, and 58.6. So gang, what I'm doing is I'm writing over here, I'm writing down the 5-number summary. So this is done. All right. Next thing I'd want to do is, do I have outliers? So remember what we do here is we create what's called our lower fence, and we create our upper fence. Remember the lower fence is the median plus 1.5 times the IQR. I'm sorry, that should be negative. And our upper fence is the median plus 1.5 times the IQR. So guys, we know that the IQR is Q3 minus Q1. Q3 is 54.85. Q1 is 47.35. So the IQR is 7.5. So our lower fence is the median, 52, minus 1.5 times the IQR, 7.5. And the upper fence is 52 plus 1.5 times 7.5. So guys, you can think of these as lower bounds for not having outliers. So guys, the 52 minus 1.5 times 7.5 gives me the lower bound on that, which is 40.75. And then I look at the plus of that to get the upper fence, and it is 63.25. Now, if I got a phone call I probably need to take, but they'll leave a message. So what I need to do now is I need to go back to my data, and I've got it from low to high. And really all I need to do, actually this is one way to do that, that's probably easiest. Just go to your list, and it's going to give you the high and the low. And we see that the low number is 42.2, which is not below the 40.75. And the high number, which we had from the 5-number summary, is not higher than the 63.25. So guys, we can conclude, therefore, from this just kind of quick analysis, that we have no outliers. And guys, we could have got that information from right there as well. Now, the next thing we do is we realize that our data ranges from 42 to 58.6, so I would create an axis here and break it up according to the numbers that I'm given. So I start at 42.2, so I think it would be reasonable to start at 40 and go to 45, 50, 55, 60, and go up to 65. What I'm going to do now is I'm going to come in and make 5 dots. 42.2 would be approximately right here. 47.35 would be approximately right there. 52 would be approximately right there. 54.85 would be just shy of the 55. And the biggest number was 58.6, which would be somewhere about right there. The box plot gets its name from making a box of the center numbers. And sometimes we call this a box and whiskers plot because it extends the whiskers in a situation like that. Remember that the distance from here to here gives us the variability for the lowest 25% of our data. From here to here gives us the variability in terms of a picture of the next 25% of our data. There's not as much variability in the third 25% of the data as there is in the first 25%. And from here to here is the other 25%. Sometimes on your assignments, you will be given other information. So let's say that we have something like this. And we have an axis that runs from 0 to 90, and we have one box plot of scores, let's say for scores A, that looks like this. And let's say that this is the distribution for question for a set of scores that we'll call B. So this is the box plot for a set of scores A, and this is the box plot for a set of scores B. Side-by-side box plots give us a comparison here. For example, what if I ask you to approximate the median for group A? Well, we come to the scores. I would bring this down to the axis, and I would see that that is at approximately a 36. What is Q3 for the scores B? Well, I'd come to the B distribution. Q3 turns out to be this line. So going back to my drawing up here, this is the minimum value. This is Q1. This is the median. This is Q3. And this is what I called it, the maximum value. So I bring a straight line down to the axis to get an approximation of those values. So Q3 would be approximately at a 60 for distribution B. Are there outliers? For distribution A, there's none. For distribution B, there is one, and its approximate value looks to me to be about a 73. So I don't know what's being measured here because I just kind of made this distribution up on the fly, but what's going on here is we can see that the scores in distribution B tend to be higher than the scores in A. We can't say anything about the mean and the standard deviation because box plots don't give us mean and standard deviation. They give us the 5-number summary. They give us the median, the IQR, Q1, Q3, and outliers, but box plots say absolutely nothing about the mean and the standard deviation. So guys, you start talking like that and we'll start taking off. You can't, that's just not cool. No, it just doesn't work. All right, guys. Very quickly, we're going to move into this video is about to end, but I want to go ahead and kind of tell you what's on the agenda, so to get this ready. What we're going to do is we are now going to be switching in this class from, at least temporarily, from samples to populations. Now, first of all, one thing we're going to run into is we're going to run into a difference in notation. If we have a mean from a sample, you should know now that the notation we use is x bar. And if we have a standard deviation from a sample, the notation we use is sx. Now, some textbooks just use an s. Not so if our data represents an entire population. If our data comes from an entire population, the mean is given as a Greek letter called mu, and the standard deviation is given as a Greek letter called sigma. So in a sample, our z-score is we take a value from our sample, subtract the mean, and divide by the standard deviation. Whereas in a population, we still take an observation from the population, but we subtract the mean and divide by the standard deviation. The calculation itself, what you enter into the calculator, turns out to be exactly the same. The interpretation is the same. It's just the notation that we use to designate the mean and the standard deviation of the population. Now, we also get into a difference of the distribution. Now, back when we were talking about samples, I told you that we could put our information in R or the graphing calculator and create a histogram. And if we got a histogram that looks something like this, what would we call it? Well, we would call it bell-shaped and symmetric. Is it perfectly bell-shaped? No. Is it perfectly symmetric? Do we draw a line down the middle and see exactly on the left side what we got on the right side? No, it's not. But we can kind of smooth this thing out and cheat a little bit to get something that is approximately bell-shaped and symmetric. And those things are specific to samples. We can collect these. We can enter this data into R or our TI-85 calculator, 83, 84, whatever calculator we've got, push the histogram button and calculate the mean and standard deviation and use this notation. It turns out that there are certain distributions in the population that are theoretically driven. And over here, when we have something that is bell-shaped and symmetric, we don't approximately have a bell-shaped and symmetric distribution. We have an almost perfect bell-shaped and symmetric distribution because we're describing a larger population. These things are called normal distributions. Normal distributions are a very, very, very important probability distribution that we encounter in statistics. And actually, this is going to be what will be next on your agenda. So what we've done so far is I've kind of gotten you ready. I forget, what was it, 3.3 or 3.4? What was it I told you that you guys would have? 3.3. Your assignment on Hawks for 3.3, this video prepared you for that. You are not yet prepared, or I think it was 4.4. I may have messed up on that. Actually, it's 6.1 through 6.4. You're not yet prepared to answer the questions on 6.1 through 6.4. Okay? So, guys, that's the end of this video. Next video, we will start on normal distributions, which is kind of cool stuff. Take care.